Section: Introduction. We're diving into the world of text generation, specifically focusing on how large language models, LLMs, process batches of sequences that often start with the same few words or phrases, known as a shared prefix. Imagine a chatbot that starts every conversation with the same greeting, or a programming assistant that begins with a standard set of instructions for every task. As these models are used more widely and on a larger scale, finding ways to handle these shared prefixes more efficiently can make a big difference. In our study, we look at this issue with an eye on the hardware that powers these models, particularly how we can make better use of the graphics processing units, GPUs, that do the heavy lifting. We notice that when sequences share a prefix, there's a lot of repetition in the data the model needs to pay attention to, which seems like a waste. Previous solutions tried to fix this by storing this repeated information more cleverly, but that didn't really speed things up much because the model still had to process each sequence's attention request one by one, which is a slow step. We introduce a new method called Hydragen, which is designed specifically for dealing with these shared prefixes. Hydragen cleverly splits the attention process into two parts, one for the shared prefix and one for the unique parts of each sequence. By doing this, it can group many sequences together and process their shared prefix all at once, using a type of calculation that GPUs are really good at, which speeds things up a lot. Our experiments show that Hydragen can make LLMs work much faster in situations where there's a shared prefix, improving the speed by up to 32 times in some cases compared to other high-performance methods. This speed-up becomes even more significant as the shared prefix gets longer and the number of sequences increases. We also explore how this approach can change the way we use LLMs. For example, with Hydragen, we can afford to use much longer shared prefixes without slowing things down too much, which wasn't feasible before. This can be particularly useful for tasks like answering questions from a long document, where Hydragen can handle many more questions in the same amount of time it would take other methods to handle just a few. Lastly, we find that Hydragen's strategy isn't just limited to a simple shared prefix scenario. It can also be applied to more complex situations where there are multiple levels of shared information, further reducing the time needed to get results. In the background section, we touch on some key concepts related to GPU performance. GPUs have a limited capacity for both calculations and moving data around. Programs can be slowed down either because they're waiting on the calculations to finish, compute-bound, or because they're waiting on data to be moved around, memory-bound. One way to measure how well a program uses the GPU is by looking at its arithmetic intensity, which is the ratio of calculations to data movements. Higher values mean the program is making better use of the GPU's computational power. Batching, or grouping together similar operations, can help increase arithmetic intensity by spreading the cost of reading data from memory across multiple operations. This is particularly effective when dealing with matrix calculations, which are common in LLMs. Modern GPUs also have special units called tensor cores that are really good at doing matrix calculations quickly, further emphasizing the importance of batching operations together. Section Summary. In this section, the authors discuss the common setting of text generation on batches of sequences, where sequences share a common prefix, and how this can impact the efficiency of large language models, LLMs. They introduce Hydragen, a specialized implementation of attention for shared prefixes, which decomposes full sequence attention into separate computations over the prefix and suffixes, leading to significant improvements in LLM throughput in large batch settings with shared prefixes. The authors also demonstrate that Hydragen's efficient processing of shared prefixes can influence algorithmic decisions on how to use LLMs most effectively, particularly in scenarios with multiple levels of prompt sharing. The authors also provide background on hardware efficiency considerations, highlighting the importance of batching to increase arithmetic intensity and reduce memory bottlenecks, as well as the significance of tensor cores in modern GPUs for efficiently computing matrix multiplications, which further motivates the batching of matrix vector products into matrix-matrix products. Section: Attention and LLM Inference. We're focusing on making attention mechanisms in large language models, LLMs, based on transformers more efficient. The scaled dot product, SDP, attention is a key part of this, working with sequences of queries, keys, and values. These sequences are represented in a way that makes them easy to handle by computers, especially during the initial stage when the model is getting ready to generate text. This stage is called the prefill stage, where the model quickly processes the starting sequence of tokens it will build on. Here, the number of queries is much larger than 1, making certain calculations particularly computer-friendly. Once the prefill stage is done, the model starts creating new tokens one by one. To speed this up, we use a KV cache that remembers the keys and values from previous tokens, so the model doesn't have to start from scratch every time. However, this changes the nature of the calculations, making them more memory-intensive and not as well suited for certain types of computer processors. When we generate text for multiple sequences at the same time, a process called batch decoding, we can make parts of the model work more efficiently, especially the parts that do a lot of calculations, like the MLP blocks. This helps us use the computer's hardware better and make the whole process faster. But attention mechanisms don't benefit as much from this batching because each sequence has its own set of keys and values, leading to many separate calculations that can slow things down, especially with larger batches or longer sequences. Also, storing all these keys and values for many sequences can take up a lot of memory. In this paper, we explore how to improve the efficiency of generating text in batches, especially when the sequences being generated share a common starting point. This commonality allows for some smart optimizations. For example, if multiple sequences start the same way, the keys and values for the shared part will be the same across these sequences. Recognizing this, we can avoid storing or processing these shared parts multiple times. We introduce a new method called Hydragen, which is designed to handle attention more efficiently when there are shared prefixes. Hydragen splits the attention calculation into two parts, one for the shared prefix and another for the unique parts of each sequence. This way, we can handle the shared part all at once, which is more efficient. We achieve this by organizing the shared keys and values in a way that lets us replace many separate calculations with a single, more efficient one. To make sure we can combine the results from the shared and unique parts correctly, we use a clever trick that involves adjusting the calculation slightly. This ensures that when we put everything together, we get the correct result. We go into more detail on how this works in the appendix of the paper. Section Summary. The section discusses optimizing attention in transformer-based LLMs, particularly focusing on attention during text generation, batched inference, and shared prefixes. It introduces Hydragen, an optimized implementation of attention for shared prefixes, achieved through attention decomposition and inter-sequence batching. By efficiently computing attention over the shared prefix and unique suffixes, Hydragen minimizes redundant reads and enables the use of tensor cores, improving the inference process for sequences with common prefixes. Section. Inter-sequence batched prefix attention. We've developed a method called inter-sequence batched prefix attention that allows us to handle attention calculations more efficiently when dealing with batches of sequences. Normally, when we calculate attention, we do it for each sequence separately, which can be quite slow. However, we noticed that if different sequences are paying attention to the same parts of the data, we call these parts keys and values, we can combine these operations into a single calculation. This is especially useful when we're dealing with a common beginning part of the sequences, known as the prefix, because the keys and values here are the same for every sequence. By doing this, we can perform one big calculation instead of many small ones, which speeds up the process because it's faster to do one large calculation on a computer than many small ones. This also means we don't have to access the memory as often to get the keys and values, which further speeds things up. However, this trick doesn't work for the unique ending parts of the sequences, or suffixes, because their keys and values are different for each sequence. We also explore a concept called hierarchical sharing. Until now, we've mainly talked about sequences that all start the same way but then become different. But what if our sequences share more complex patterns, not just a simple common start? For example, some sequences might share not just a beginning but also some middle parts, forming a sort of tree structure where each branch represents shared sequences. We've adapted our method to handle these more complex scenarios as well, allowing us to efficiently calculate attention in cases where the shared parts of sequences form a tree. When it comes to seeing how much our method, which we call Hydragen, can speed up calculations, it really depends on how big of a role attention plays in the overall process. If attention calculations are a major bottleneck, then Hydragen can significantly speed things up. However, if the bottleneck is elsewhere, like in reading model parameters from memory, then Hydragen won't make as much of a difference. The size of the batch and the length of the sequences also affect how much Hydragen can help. Interestingly, Hydragen is more beneficial for models that use a specific type of attention called multi-headed attention compared to other types. This is because Hydragen can make better use of the computer's hardware, leading to faster calculations. For our experiments, we implemented Hydragen in a straightforward way using PyTorch, a popular programming framework for deep learning, and didn't need any specialized computer code. This simplicity means it could be easily adapted to work on different types of computer hardware. We used two different tools for calculating attention on the prefix and suffix parts of the sequences, ensuring that our method works well even as the sequences change over time. Section Summary. The inter-sequence batched prefix attention technique allows for efficient computation of attention over a shared prefix for a batch of sequences by batching every sequence's query vector together into a single attention operation over a single sequence, significantly improving hardware utilization and reducing the number of times the prefix KV cache is read from GPU memory. This method can be extended to more complex sharing structures, such as tree-like sequences, and can lead to improved decoding speed, especially in models with multi-headed attention and larger batch sizes. The implementation of Hydragen is simple and can be easily ported to other hardware platforms, such as TPUs, due to its reliance on PyTorch and fast attention primitives. Section. End-to-end throughput. We tested the overall performance of our language model, Hydragen, by seeing how well it could handle a lot of tasks generated from a single starting point. This approach is often used to enhance a model's problem-solving skills, especially for complex tasks like math or coding competitions. We compared Hydragen's performance with 4 other methods. 1. Flash attention. Here, we treated each task as completely unique, without any tricks to speed things up by recognizing similarities between them. This method quickly ran into memory issues because it had to store a lot of repetitive information. 2. VLLM. This method used a smarter way to handle repetitive information, which let us test it with more tasks at once. It also read through the starting information more efficiently, saving time and resources. 3. VLLM without detokenization. By turning off a feature that breaks down the tasks into smaller pieces, we noticed an improvement in how fast it could process tasks. 4. No attention. This unrealistic method skipped a crucial step in understanding the tasks but showed us the fastest possible processing time, helping us understand the cost of certain operations. We ran our tests on a powerful setup involving 8 high-end GPUs, which allowed us to handle a lot of data at once. Our findings showed that when dealing with a small number of tasks, all methods were somewhat close in performance. However, as we increased the number of tasks, Hydragen started to outshine the others, especially when the starting point contained a lot of information. Further tests showed that Hydragen's performance remained strong even as the starting point grew significantly, always staying close to the ideal speed set by the unrealistic, no attention, method. We also did more detailed tests with different settings and found that Hydragen could be over 50 times faster in some cases. In another set of tests focusing on how Hydragen handles attention to different parts of the tasks, we found that it does particularly well as the amount of starting information increases. However, the length of the additional information added to each task also affected the speed, with longer additions slowing things down. This slowdown was more noticeable on certain types of hardware, suggesting that Hydragen benefits from a balance between processing power and memory speed. Lastly, we tested Hydragen on a task involving answering questions from a very long document. We embedded fake facts into a section of War and Peace and asked the model to answer questions based on these facts. Hydragen performed impressively, staying close to the ideal speed and handling many more questions in the same amount of time it took other methods to handle just a few. In summary, our tests show that Hydragen is highly efficient, especially for tasks with a lot of starting information, and it holds up well even as tasks become more complex. Section Summary. This section discusses the benchmarking of end-to-end LLM throughput, comparing Hydragen against 4 baselines. It highlights that as the batch size grows and attention over the prefix becomes more expensive, Hydragen significantly outperforms the other baselines. The micro-benchmarks also demonstrate that the speedup with Hydragen increases as the batch size and prefix lengths grow, but the suffix length has a significant impact on inference time, with throughput decreasing over time as the lengths of completions grow. Additionally, the performance of Hydragen on workloads involving very long documents is explored, showing that Hydragen's processing time always remains within 75% of the no attention optimum, even outperforming the flash attention baseline in processing a larger number of questions. Section: Hierarchical sharing in competitive programming. We want to share how we explored the advantages of using Hydragen in a competitive programming environment, which involves a structure where information is shared in a hierarchy. The idea to create Hydragen came from the challenge faced in competitive programming, where the current top systems generate a huge number of potential solutions based on prompts that can be very long, sometimes containing thousands of words. In our experiment, we tested how long it took to evaluate a tool called CODELLAMA7B on 120 problems from a dataset known as apps. We did this by giving it a prompt with 2 examples, 2-shot prompt, and generating 128 possible solutions for each problem. When we process multiple problems together, we notice that some parts of the prompts overlap. This overlap happens in 2 ways. The 2-shot prompt is the same for all problems in the group, and each problem's description is reused for all its potential solutions. We tested 2 different ways of using Hydragen in this setup. 1. Single-level Hydragen. Here, we only shared the 2-shot prompt across all problems but didn't share the problem descriptions among the potential solutions. This meant we ended up storing the same problem description many times, which limited how many problems we could work on at once. 2. 2-level Hydragen. In this approach, we shared information at both levels. This not only made the process more attention efficient by increasing how much we could share but also avoided storing the same information multiple times. This allowed us to work on more problems at the same time. We tested this method with both the original number of problems and a larger group to clearly see the benefits. Our findings showed that even when we didn't increase the number of problems, just adding another level of sharing with Hydragen made the evaluation process 18% faster because it was more efficient. Moreover, by not having to store duplicate information, we could increase the number of problems we worked on, which cut down the evaluation time by an additional 45%. In this paper, we introduced Hydragen, a precise and hardware-aware way to handle attention in situations where there are batches of sequences with common beginnings. Our method separates the attention needed for these shared beginnings from the attention needed for the unique endings. This lets us handle attention for the shared parts all at once, which saves memory and makes use of specialized hardware features. Hydragen is especially useful in situations where managing attention is a big part of the time needed to generate text, especially when there are many sequences with long shared beginnings and short unique endings. We see Hydragen as a tool that can be added to larger systems, not as a standalone solution. We're excited about the possibility of incorporating Hydragen into systems that continuously handle requests and organize sequences in a way that takes advantage of overlaps. We believe our work will inspire new algorithms that efficiently manage shared beginnings in text generation. Hydragen's ability to handle larger shared beginnings without slowing down could allow for providing much more context than before, which could be very useful in research and in solving complex problems with language models. We also discussed related work in the field, highlighting how transformers and language models have evolved, the challenges of managing large caches of key value pairs in these models, and how some approaches are trying to make these systems more efficient by understanding and leveraging the hardware they run on. Our work adds to this by focusing on optimizing attention in sequences with shared parts, which can make these models faster and more efficient.